Okay, well, it's a pleasure to welcome you back to the swampland. I just realized that in the previous meeting 3 years ago, on 27th September, I was the last chairman. So maybe the organizers thought that we should continue where we stopped last time. Uh, the first speaker couldn't make it, so we'll start immediately with the second speaker. And the second speaker is Tom Rudelius, and he will talk about sharpening the distance conjecture in diverse dimensions.
Great. Yeah, my slides, I guess. Great, thank you. Okay, great. Thank you very much to the organizers for the invitation to speak here and for putting together what promises to be a very exciting workshop. I think I speak for everyone here when I say that it's a great joy to be able to be back here together in Madrid and to be able to have these workshops again. So my talk today is going to be based primarily on some recent work and some work to appear with Muldrow, Etheridge, Ben Heinrich, Sami Kaya, and UAQ. A quick outline for where we're headed today. I'm going to start up by introducing and proposing a sharpened version of the distance conjecture. We'll then see evidence for this conjecture. Oh. Okay, great. So I'll start out by proposing a sharpened version of this conjecture. We'll then see evidence for this conjecture, and we'll study its implications. So to begin, probably most people here are familiar with the distance conjecture of Oguri and Vafa. Supersymmetric quantum gravity theories in general have moduli spaces of vacua parametrized by scalar fields. And the claim of the distance conjecture is that as some vacuum expectation value of a scalar field goes to infinity, that there will be some tower of particles beginning at some mass scale, which will be exponentially suppressed with the VEV of the scalar field phi, where here lambda is some coefficient. And this lambda is going to play the starring role in this talk. So it's long been understood, going back all the way to the original work of Oguri and Vafa, that this coefficient lambda should be order 1 in Planck units. However, the precise values that are allowed for lambda has been a subject of much discussion and debate. So the point of this talk is to propose a new lower bound on the lambda of the lightest tower in a given infinite distance limit, namely lambda is greater than or equal to 1 divided by the square root of d minus 2. So note here that a typical infinite distance limit will typically have multiple towers that are becoming exponentially light, and they'll have different lambdas. The claim here is that there's always at least one tower with a lambda that satisfies this bound. There may be other towers with smaller lambdas that do not. One thing worth noting is that our arguments actually also point to an upper bound on lambda, but for sake of time, I'll focus on the lower bound here. A quick aside, an important role in this talk will be played by the emergent string conjecture of Lee, Lerche, and Weigand. This conjecture holds that any infinite distance limit should either be a decompactification limit accompanied by a tower of Kaluza-Klein modes, or an emergent string limit accompanied by a tower of string oscillator modes. We'll see that it's not quite right to say that the sharpened distance conjecture implies the emergent string conjecture or vice versa, but we'll see that these two conjectures do nonetheless go hand in hand. So when combined, a very simple and consistent picture for infinite distance limits in moduli spaces emerges. So with this, let me get on to the evidence for this sharpened distance conjecture. Let me say that I will, throughout this talk, refer to the sharpened distance conjecture as the bound lambda greater than or equal to 1 over square root of d minus 2. So the first line of evidence is dimensional reduction. Many of the most well-supported swampland conjectures have the property that they're exactly preserved under dimensional reduction. Perhaps the most famous example of this is the weak gravity conjecture, this bound on the charge to tension ratio of a p-brane in terms of some order 1 coefficient gamma. And this coefficient gamma has the property that it's exactly preserved under dimensional reduction. If you start with some theory, it has some gamma, you reduce on a circle, you'll find that gamma is unchanged. This ensures that the higher dimensional theory satisfies the weak gravity conjecture if and only if the lower dimensional theory does as well. Turning this around, if one didn't know what the right value of this order 1 coefficient gamma was, one could actually derive the value that appears in the weak gravity conjecture bound simply by demanding consistency under dimensional reduction. So at least in this case, dimensional reduction is a useful tool for determining these order 1 coefficients. And thus it makes sense to try to apply this to the distance conjecture as well. So we'll start out by assuming that in capital D dimensions, we have a tower of particles that satisfies the distance conjecture in the limit as phi goes to infinity with some order 1 coefficient lambda that we're about to determine. Now, we could actually perform the same argument for a general compactification on an n manifold, but for simplicity today, we'll just consider compactification on a circle to little d equals big D minus 1 dimensions. This tower that we started with in capital D dimensions will give rise to a tower in little d dimensions. We'll have the same scaling with the dilaton phi, but now we'll also pick up some scaling with the radion rho, which measures the size of this extra dimension. If we then define a linear combination of this and canonically normalize, we can rewrite this in terms of this new field phi prime, and now we define lambda d to be this coefficient here. This gives us a relation between lambda sub little d and lambda sub big D, and one can easily check that this is solved by setting lambda equal to 1 over the square root of d minus 2. This is our first hint that there's something special about this value. It is exactly preserved under dimensional reduction. Now, further reasons to believe that there's something special about this value come when we consider the Kaluza-Klein modes in this compactification. So if we start out with a tower of particles in the parent theory and we reduce, we'll get the tower that we already discussed in the lower dimensional theory, but we'll also have a tower of Kaluza-Klein modes. The masses of these Kaluza-Klein modes do not depend on the dilaton phi, but they'll scale with the radion rho with this strictly larger coefficient. In visualizing this scenario, it's helpful to define these so-called scalar charge to mass vectors, which are given by the negative of the logarithmic derivative of the mass with respect to the scalar field I. So for instance, for these Kaluza-Klein modes, there's no dependence on the dilaton phi. So the first entry here is just 0. But then there's this dependence on rho with this coefficient square root of d minus 1 over d minus 2. Hence, this vector for the Kaluza-Klein modes is 0, comma, square root of d minus 1 over d minus 2. And if we assume that the higher dimensional theory has a tower of particles which saturates our proposed sharpened distance conjecture, lambda equals 1 over square root of d minus 2, we find that this tower of particles has a zeta vector given by this point here. Now, what is this figure telling us? Well, suppose that we want to consider the limit where phi is held fixed and rho goes to infinity. So in the phi rho plane, we're heading in the vertical direction here. What this is telling us is that the lambda coefficient of the lightest tower in this limit is going to be given by the length of this segment here between this point and the origin. This length is, in fact, square root of d minus 1 over d minus 2. And this is what we just saw. In the limit as rho goes to infinity at fixed phi, we have a tower of Kaluza-Klein modes with lambda equals to this value. Likewise, if we were to go off to infinity in this other direction here, with phi and rho going to infinity with this fixed ratio, then the lambda coefficient of the latest tower is given by the length of this segment, which is 1 over square root of d minus 2, which lies on this ball of radius 1 over square root of d minus 2. And more generally, if we go off to infinity in this diagonal direction in here, the lambda coefficient of the latest tower will be given by this line segment. It'll lie between these two values, and it's the lambda value associated with the Kaluza-Klein modes in this direction. So in this perspective, the statement of the sharpened distance conjecture is equivalent to the convex hull condition, that the convex hull of these scalar charge to mass vectors should contain this ball of radius 1 over square root of d minus 2. Now, from these two towers alone, you see that the convex hull condition is not satisfied in all directions. It's satisfied between here and here, but if we were to say take rho to negative infinity or take phi to negative infinity, we need some additional towers. In practice, these additional towers will come from string winding modes. So here we're considering a simple toy model suppose that we have some string in capital D dimensions whose string oscillator modes saturate the sharpened distance conjecture. Lambda is equal to 1 over square root of D minus 2. We're also going to assume that there's an S dual string, resulting in these mirror symmetric figures here. So what this means is that after we reduce, we'll get the towers of Kaluza-Klein modes, the towers of string oscillator modes, and the S dual string oscillator modes, and also the winding modes and the winding modes of the S dual string. Together, you see that for general D greater than or equal to 4, the convex hull condition, and therefore the sharpened distance conjecture, will be satisfied. In fact, we actually learned something else very interesting from these figures. You'll note that there are certain points of tangency here, where the sharpened distance conjecture is exactly saturated. Lambda is equal to 1 over square root of D minus 2. And you'll note that all of these limits are characterized by the presence of string oscillator modes that saturate this bound. This is true even in 5 dimensions, where we have this additional point of tangency, but also we have the oscillator modes for a magnetic monopole string. So what we're learning from this is not only is the sharpened distance conjecture satisfied in these simple toy models of dimensional reduction, but in fact, it's saturated if and only if the limit in question is an emergent string limit. Thus, in the language of the emergent string conjecture, we're led to the belief that the sharpened distance conjecture should be saturated in emergent string limits and satisfied comfortably in the other limits, which are decompactification limits. So this is our expectation just from the simple model of Kaluza-Klein reduction. Now we can see how this actually works in string and M theory. So we'll start out with your favorite 10-dimensional supersymmetric string theory. In the weakly coupled limit, as phi goes to infinity, there will be a tower of string oscillator modes that actually exactly saturate the bound. They have lambda equal to 1 over square root of D minus 2. By S duality, for some of the string theories, we find the same scaling behavior in the opposite emergent string limit, where we have an S dual string that's becoming tensionless. And in the other string theories, the phi goes to negative infinity limit is a decompactification to 11-dimensional M theory, characterized by a tower of Kaluza-Klein modes with this strictly larger coefficient, which satisfies the sharpened distance conjecture with room to spare. Indeed, as expected, emergent string limits saturate the bound. The other limits are decompactification limits, which satisfy it comfortably. If we start with 10-dimensional type 2b string theory and we reduce on a circle, we'll find exactly this figure that we had before. And if we continue playing this game, reducing type 2b string theory down to 9, 8, 7, 6, 5, 4 dimensions on a torus, this is now maximal supergravity, backtified on a torus, or so maximal supergravity in d dimensions. And the UMass Amherst contingent of our collaboration through heroic efforts showed that in all of these cases, the bound lambda is greater than or equal to 1 over square root of D minus 2 is indeed satisfied in all limits and saturated in emergent string limits. You might say, well, this is all maximal supergravity. What about some examples with less supersymmetry? So this is work in progress. And we have not yet checked every infinite distance limit of type 2A or type 2B string theory on K3. But what I've shown here is the dilaton volume modulus plane. And you can see that indeed, the scalar charged mass vectors have a convex hull, which contains this ball. And the places where the sharpened distance conjecture is saturated correspond to emergent string limits with towers of string oscillator modes. Okay, next I want to switch gears a little bit and talk about some bottom-up evidence for this conjecture. And for sake of time today, I'll focus exclusively on 5 dimensions. 5-dimensional supergravity is controlled largely by a cubic function known as the prepotential. Here, these yi's are homogeneous real coordinates, which are homogeneous in the sense that they're identified under simultaneous rescaling. What we're going to do then is restrict our attention to straight line paths in the space of these homogeneous coordinates, such that each of these yi's is a linear function of some parameter s. We're going to assume that the limit as s goes to 0 is an infinite distance limit. And it's not hard to show that this implies that the prepotential in homogeneous coordinates must vanish in the limit s goes to 0. And because of the assumption of straight line paths, it must vanish either linearly in S or quadratically in S. In the first case, where the prepotential vanishes linearly in S, we can use the relationship between the prepotential and the gauge couplings to show that the smallest gauge coupling will scale on this limit with some canonically normalized scalar field rho in the S goes to 0 limit, which is the rho goes to infinity limit, with this coefficient here. And the largest gauge coupling will scale like so. Here we need to invoke appropriate versions of the weak gravity conjecture. So for this gauge field, we invoke the tower weak gravity conjecture, which tells us that we should have a tower of particles beginning in a mass scale which is bounded above by this expression here, this coefficient matching this one. And we can apply the magnetic weak gravity conjecture to the strings charged magnetically under this gauge field, and we find this coefficient. Now, these coefficients here are actually very familiar to us from our dimensional reduction analysis. This is exactly the coefficient that we had for the tower of Kluge-Klein modes with the radion. And this is the same as the coefficient of the tower of string oscillator modes. If we start with the tower of string oscillator modes in one higher dimension and reduce on a circle, we get this coefficient here. In other words, we have exactly the sort of scaling that we expect for a decompactification limit. This is emerging just simply from the structure of minimal supergravity itself under the assumption of these appropriate versions of the weak gravity conjecture. Already this has built into it what we need for the emergent string conjecture and the sharpened distance conjecture to be true. Second case, we can do the same sort of analysis. Here, we find the 1/squared of d-2 scaling for both this tower and the tower of string oscillator modes. This is exactly the scaling that we expect for an emergent string limit. And then the same story applies also in d equals 6, 7, 8, 9, and 10 dimensions as well. In all of these cases, assuming these appropriate versions of the weak gravity conjecture, we find, just by studying how the gauge couplings scale with proper field distance, either we have the 1/squared of d-2 scaling expected for an emergent string limit, or we have this scaling expected for the Kluge-Klein limit, the decompactification limit, or we find ourselves in some intermediate regime between the two, so somewhere along this line segment. Indeed, if we drop the assumption of straight line paths in 5 dimensions, we'll end up somewhere along here, in between this point and this point. All of this, of course, fits perfectly with the sharpened distance conjecture and the emergent string conjecture. It suggests that a generic infinite distance limit falls somewhere along this line, corresponding to a decompactification or emergent string limit with lambda greater than or equal to 1/squared of d-2. Finally, the last bit of evidence I want to consider is a reevaluation of naive counterexamples in 4 dimensions. So a number of previous works studying infinite distance limits in 4 dimensions have found towers with lambda equals 1/squared of 6, which naively seems to violate our proposed bound because 1/squared of 6 is less than 1/squared of d-2. However, once again, this value is very familiar to us. This is the 4-dimensional version of 1/squared of d-1 times d-2, which is exactly what we saw if we had a tower of charged particles or tower of string oscillator modes. We reduce on a circle. We find that this tower will now have this same dependence on the radion rho. However, we also found that these same limits have a tower of Kluge-Klein modes with a strictly larger coefficient lambda equal to square root of d-1 over d-2, which in 4 dimensions is the square root of 3/2. In other words, what this analysis suggests is that any time that we have a 1/squared of 6 tower in some infinite distance limit in 4 dimensions, it should be accompanied by an even lighter tower with lambda equals square root of 3/2, corresponding to Kluge-Klein modes in some duality frame. This latter tower ensures that the sharpened distance conjecture is satisfied, because remember, the conjecture is not a conjecture which necessarily applies to every tower in an infinite distance limit, but rather to the lightest tower. So this is our expectation. Now let's see how this actually works in examples. So in 2019, Joshi and Clem had a very nice paper studying various infinite distance limits in Calabi-Yau moduli spaces. In one infinite distance limit, they found this tower with lambda equals 1/squared of 6. But more generally, they found a mass formula in terms of 2 integers, x and y. You'll see here that as y varies over 1, 2, 3, and so forth, this term here gives us a lambda equals 1/squared of 6 scaling. However, if we simply set y equals 0 and let x vary, we find a tower of particles with a square root of 3/2 scaling. Indeed, exactly what we expect from our dimensional reduction analysis, exactly what we expect from the emergent string conjecture. This corresponds to a decompactification limit to 5 dimensions, and the sharpened distance conjecture is satisfied. In another very nice paper, Gandler and Valenzuela really pioneered what I've called the bottom-up approach in this talk, studying how gauge couplings scale with proper field distance, using this to relate the tower weak gravity conjecture to the distance conjecture. They studied a couple of 4-dimensional examples, one of which actually saturates our proposed bound, lambda equals 1 over square root of 2. The other one takes this form, and they studied the scaling of the gauge couplings. They found that one gauge coupling scales with this 1 over square root of 6 scaling, which by the tower weak gravity conjecture should give us a tower with lambda equals 1 over square root of 6. However, the same example has another gauge coupling, which has the square root of 3/2 scaling. Indeed, if one imagines a 5-dimensional supergravity theory that has no vector multiplets, only one vector boson in the gravity multiplet, and then reduces on a circle, then this gauge coupling coming from the 5-dimensional gauge field will scale like so, and the Kaluza-Klein gauge field will have a coupling that scales like so. The Kaluza-Klein modes then will satisfy the sharpened distance conjecture in this limit. Okay, so I've given what I hope is compelling evidence that this sharpened distance conjecture is true. Now I want to talk about some of its implications. And the first one I want to discuss is the implications for asymptotic scalar field potentials. It's long been observed that scalar field potentials in quantum gravity seem to fall off exponentially in asymptotic regimes. So as phi goes to infinity, the potential will decay exponentially, suggesting a bound on the gradients in these asymptotic regimes of this form. Again, let me stress that the key phrase here, in asymptotic regimes. This doesn't necessarily apply everywhere in scalar field space. Now, like lambda min, the minimum value of the distance conjecture coefficient, the minimum value of this coefficient is also often debated. But from our analysis so far, we're now in a position to determine this value under a few assumptions. So first of all, let's assume that the sharpened distance conjecture applies beyond just massless moduli to scalar fields with potentials as well. This extension also goes back all the way to the original work of Ogre-Vafa. Since then, there seems to be some evidence for it, but it is an assumption that remains to be completely justified. We're further going to assume that not only is this bound satisfied in these infinite distance limits in scalar field space, we're going to assume that the towers that do so are either Kaluza-Klein towers or towers of string oscillator modes, as suggested by the emergent string conjecture in our analysis in this talk. Put together, what this tells us is that either the string scale or the Kaluza-Klein scale is going to be bounded above in the limit as phi goes to infinity by this 1 over square root of d minus 2. If we then assume that the potential scales exponentially with some number c in this limit, then as long as this coefficient c isn't too large, which is the case of interest to us, then the Hubble scale will go simply like the square root of v. This doesn't rely on any sort of slow roll approximation. This is just simple scaling behavior. So finally, if we put these together and we demand that the Hubble scale should be bounded by the string scale and the Kaluza-Klein scale, then we find that c is bounded below by 2 divided by the square root of d minus 2. Now, this is a very familiar result. It's actually one that I've argued for in a series of recent works, and it has an important physical significance. This bound is equivalent to the strong energy condition in these asymptotic limits. It forbids accelerated expansion of the universe in these limits. It's exactly preserved under dimensional reduction in the same way that the sharpened distance conjecture is. It's satisfied in all infinite distance limits with a supersymmetric vacuum. And at least in my opinion, it likely points to the fact that quintessence, like de Sitter, is at best metastable in quantum gravity. It's long been believed that de Sitter vacua, assuming they exist in the landscape, cannot exist indefinitely, but must decay after a finite time. This result seems to suggest that the same thing is likely true of quintessence. Perhaps quintessence can occur, accelerated expansion can occur, in the interior of scalar field space for a finite period of time, but it can't occur arbitrarily far out in scalar field space for an indefinite period of time. The quintessence, like de Sitter, is likely at best metastable. Now, there are some caveats in this argument here. One thing to, again, stress is that this bound has really focused on the asymptotic behavior of the potential. I'm certainly not trying to say that accelerated expansion can't occur anywhere in quantum gravity, because after all, we live in a world that is experiencing accelerated expansion at the moment. Now, the bound that we've derived on this coefficient C may be violated in principle if we drop the assumption that the Hubble scale is below the Kaluza-Klein scale and the string scale. But there is a price to be paid if we drop the assumption. If the Hubble scale drops below the string scale, then effective field theory, if the string scale drops below the Hubble scale, then effective field theory breaks down altogether. If the Hubble scale is larger than the Kaluza-Klein scale, it means that we really don't have a d-dimensional cosmology, because the horizon size is actually smaller than the size of these extra dimensions. Finally, note if there are multiple scalar fields, we're not bounding the derivative with respect to any particular scalar field. We're really bounding the gradient of the potential. Now, this argument can be specialized with a few slightly more assumptions to the case of 4 dimensions, where it can have important consequences for large field inflation. So we're going to assume, once again, that either the string scale or the Kaluza-Klein scale is bounded above by this exponential. Here, we're also going to add the additional assumption, which remains to be justified, that it's suppressed relative to the Planck scale, as opposed to some other arbitrary mass scale. Now, large field inflation in our universe, if it occurred, requires a Hubble scale of about 10 to the minus 4. Plugging this in to this inequality, this tells us that the field traversal is bounded to be less than about 14 m Planck. And this is actually a phenomenologically interesting bound. For instance, it would tell us that m squared phi squared inflation is in a swamp. And more generally, it leaves very little room for the required hierarchy of scales in a controlled model. One caveat here, aside from the additional caveats I've already mentioned, it's less clear that this argument applies to periodic scalar fields like axions. Now, there are a number of other interesting applications of the Sharpening distance conjecture that I'm not going to have time to discuss today. It has interesting consequences for the repulsive force conjecture, the scalar weak gravity conjecture, axion couplings to matter, the refined distance conjecture. I also didn't have any time to talk about the upper bound on lambda, but you can see our recent work in forthcoming papers for more details. So in summary, the main thing to remember for my talk is this new proposed sharpened distance conjecture, which holds that the parameter lambda of the lightest tower in an infinite distance limit is bounded below by 1 over the square root of d minus 2 in d dimensions, with saturation occurring only in emergent string limits. We've seen strong evidence for this bound in this talk, coming from the fact that it's preserved under dimensional reduction, examples in string theory supergravity, resolution of apparent counterexamples to the bound in 4 dimensions, and perhaps most importantly, the connection to the emergent string conjecture. I think from what we've seen today, our Kaluza-Klein reduction analysis, it's very hard for me to imagine a counterexample to this conjecture that wouldn't also be a counterexample to the emergent string conjecture. Finally, we've seen that this bound may have important consequences for large field inflation, scalar field potentials, and notably, it rules out accelerated cosmological expansion in asymptotic regions of scalar field space. Thank you.
Okay, are there any questions there in the back? Just wait for the microphone.
Thank you. In the work we had related to the de Sitter conjecture and the TCC, we found a surprising, well, maybe not so surprising, but a sort of counterexample to all these bounds in d equal 3. You haven't really mentioned d equal 3. Do you have anything to say about it?
Yeah, that's a really good question. I have not thought too much about the conjecture D equals 3. Something that is very evident from this conjecture is the fact that it definitely breaks down in 2 dimensions, because 1 over the square root of D minus 2 diverges there. So I think what we're definitely seeing here is sort of built into the conjecture is a lower bound on the number of dimensions where this might apply, but 3 remains a mystery. I think it definitely seems to be true in 4 dimensions from what we can tell, but 3 dimensions is more mysterious, and I guess I wouldn't wager too heavily either way in that case. Thanks. Yep, that's a good point.
Hi, thank you, Tom, for the talk. I think it's very nice how the whole story, how it's written. But let me ask a few questions. So, for instance, in the case of 4D n equals 2, that we were talking about this 1 over square root of 6, you said now that you find other Kaluza-Klein towers that are lighter, but I imagine that you don't mean Kaluza-Klein towers in the type 2B compactification because the volume is fixed. Do you mean like the M-theory Kaluza-Klein towers? Or which ones you find?
Thanks. Yeah, that's a good question. When I say Kaluza-Klein towers, I mean Kaluza-Klein towers in some duality frame. So I'm thinking here in terms of the emergent string conjecture, which suggests that every limit should either have a tower of string oscillator modes or a tower of Kaluza-Klein modes. In a given duality frame, that tower of Kaluza-Klein modes may not look like a tower of Kaluza-Klein modes. For instance, compactifying a circle, take that circle to small volume. You say we don't have a tower of Kaluza-Klein modes, we have a tower of winding modes. But the point of the emergent string conjecture is that in some other duality frame, it's a tower of Kaluza-Klein modes. Here, I'm sort of invoking that implicitly.
So which ones? Like from what, in what duality frame?
I guess what I might think is perhaps there's that invoking mirror symmetry, there would be a duality frame in which these modes are Kaluza-Klein modes. I guess what I'm really saying here is that there's a tower with lambda equals square root of 3 halves, which is exactly the scaling expected.
But what tower? I mean, what states do you mean? Like you expect that there is a tower, or you find a tower? Like which one?
Oh well, okay. So in the example with Joshi and Clem, we found a tower. In your example, we found a tower in the same way that you found a tower, which is implying that invoking the tower regravity conjecture for a given gauge field.
Okay.
I mean,
the whole point is that, I mean, I can imagine that you think like, yeah, other wrapping DC brains, that's like, I mean, if you take the BPS mass, of course, like already in the original paper with Thomas and Eran, we know that there are other BPS states that will have an exponential rate, which is larger, like the square root of 3 half. But the whole point is that the tricky part for the distance conjecture is to show not just the scaling of the mass, but that there is an infinite tower of states, because BPS states, I mean, not always are populated. And that's why we were focusing on the 1 over square root of 6, because there with the monodromy, we could really argue for the infinite tower. And I'm wondering how to even argue, for an infinite tower with a different exponential rate, because then the monodromy does not apply. And it's really a very hard question, like to show the distance conjecture there, that is a tower.
Yeah. I mean, I agree that in a given example, it might not be easy to demonstrate the existence of this tower. I think in the examples that we've looked at, like in that Joshi-Clem example, they give stability conditions for stability of the BPS states, and all of the ones in the tower I discussed are stable. They exist. That tower exists.
Yeah, that's like the large volume, so that's easy. Yeah.
Right. More generally, I'm not sure. I think that this is now again where I say, I think that perhaps one of the most compelling lines of evidence for me is the connection with the emergent string conjecture. It's possible the emergent string conjecture is false, in which case I'm not sure if one would expect a tower of Kaluza-Klein modes. Okay. But if it is true, then I would expect such a limit would correspond to a tower.
A very cool evidence, like if we can find such a tower in those 4D n equals 2. I mean, that would be nice.
Yeah. I mean, I agree. It could be hard in a given example to find the actual or to prove that there is a tower. Yeah.
So yes, I have 2 comments. Thanks, Tom, for the nice talk.
Yeah.
So okay, there is always a debate which cutoff we should take, either like the species scale. I saw that, for example, for your application to this asymptotic scalar potential inflation, you take like MKK M strings, but in principle, the species scale would be higher, some orders higher. and you would get different bounds on
Yeah.
C, right?
Yeah.
Yeah. Okay.
Good. Okay.
Because
Sorry.
Yeah, no, because you justify this like you say like we wouldn't have like a d-dimensional cosmology. Still, like in the context of asymptotic scalar field potential, you could still like get an interesting bound, a different bound from what you got there.
Yes. Yes, I agree. Yeah. So in our paper, what we first consider the species bound, and obviously because that can be higher especially in the case of the Kaluza-Klein tower, the bound can be weaker. However, I think sort of a big lesson of the last few years in looking at this, especially from the emergent string conjecture, is that these towers that we seem to find aren't just some sort of arbitrary towers of particles. They seem to either be towers of string oscillator modes or towers of Kaluza-Klein modes. To me, that's very interesting because, especially, I mean, if it's a tower of string oscillator modes, the species bound scale will be roughly the string scale. But if it's a Kaluza-Klein tower, the species bound scale can be much higher. However, if we're talking about the cosmology, it really doesn't make sense to talk about cosmology if the extra dimensions are larger than the Hubble scale. I mean, we can talk about cosmology, but it's not a d-dimensional cosmology. We really have a decompactification. So I think that's how we can justify in this particular case using a stronger bound, because we're assuming here that we don't have a decompactification. Yeah.
Okay. Yeah. A second comment was that the fact that m square phi square is in tension with swampland was already pointed out actually 4 years ago by me and Irene in a paper.
Okay. Thanks.
Yes.
Thanks for pointing that out.
Shorten here the discussion section. I'm supposed to ask if there are any questions from the online audience. Okay, that goes very fast then. So then, I guess we have a coffee break now, right? Okay, very well. Let's thank the speakers again.